Dear students, welcome you all to lectures on friction. In the first phase, I will give a brief introduction of the friction mechanism and basic theories. And I will solve some worked out problems so that to support the basic theories. In the next phase, I will again give lectures on friction where I will talk about the application of friction in various machine elements. Well, to begin with, I have shown you in this particular slide the famous portrait titled Mona Lisa, which requires no introduction, and all of you know that this is probably the most discussed work of art ever. And the creator of this magnificent piece of art is Leonardo da Vinci, that also you know. Now, apart from art, the innovative mind of Leonardo da Vinci probably led him to venture in the world of science also. In the present context, you will be surprised to know that the original contribution on the study of friction was carried out by Leonardo da Vinci. He did a lot of experiments and he could figure out some quantifiable investigations of friction, and also he contributed on two fundamental laws of friction. Leonardo was fully familiar with basic concepts of friction, lubrication, and wear, which taken together is known today as a subject called tribology. Just for your understanding or for your knowledge, I would like to say the word tribology derives from the Greek word tribos, which means rubbing. In literal sense, it is the science of rubbing. And Leonardo da Vinci contributed a lot on this subject, and he worked for around 20 years in different phases to find out or to investigate the findings on friction. Can you understand that, or can you imagine that the word tribology came into existence or being used by later scientists almost 450 years after the death of Leonardo da Vinci? So this shows that what was a talented man he was. He was he was pioneer in the works of art, and also his contribution to the science people now recognize in a fullest form. Unfortunately, Leonardo never published his findings on friction, and obviously he did not get any credit for his wonderful works. However, he maintained a notebook where he had noted down all his findings with sketches and with meticulous writing. He studied on the subject of friction for simple blocks, screw threads, wheels, and many more, which are evident looking at his notebook. Now, This is one of the sketches which I have got from this particular reference and reproduce over here to show you his meticulousness of drawing the sketch for an friction apparatus. Leonardo basic laws of friction stated in 1493 were later articulated by Amundsen and Coulomb. You must have heard the name of Coulomb because you have done Coulomb's laws of friction in your school days. The statements are very simple. That is, the force of friction acting between two sliding surfaces is proportional to the load pressing the surfaces together, and the force of friction is independent of the apparent area of contact between the two surfaces. I will touch upon this second point later in one of the slides. However, this is known to you that the force of friction divided by the weight, which normally we do not put weight, but we just represent as a normal reaction, is equals to mu, which happens to be the coefficient of friction. Now, this reference, what I just told about, was published in 15th August 2016, just only 4 years back from now. So you can understand that still the works of Leonardo da Vinci attracts people, attracts scientists. Okay. And this particular person, Mr. M. Hutchings, he compiled in his work, this particular work, Leonardo da Vinci Studies of Friction. Now you understand that how important his works on friction was. So that's the reason I prefer to introduce Leonardo's contribution in the study of friction. Now, whenever one contacting surface has a tendency to slide over another surface, the tangential force generated between the contacting surfaces is known as friction force. And it always opposes the cause which creates a tendency to slide. Now, this is the basic law of friction which you should keep it in your mind because this is important while drawing the free body diagram for solving some problems where you should be drawing the friction forces in such a manner that it always satisfies this simple law of physics. However, there are also certain conditions to be satisfied that we will talk about at the later stage. In machines and processes such as bearings, power screws, gears, flow of fluid through pipes, etc., we always want to reduce the friction because that will always give you a better system efficiency. In this context, lubrication is also used to reduce friction between the mating parts of the machines. And the reason is as I have just stated. Whereas in certain situations like brakes, belt drives, car tires, even in shoes used for normal walking, we look for maximization of the friction. This particular part also we will touch upon that as an application of friction at the later stage. The result of friction is that there is a loss of energy which is dissipated in the form of heat, and the mating parts will be subjected to wear. Now, this wear also comes out to be an important parameter in the study of friction. However, this is beyond our scope of study at this present course. Let us look at the types of frictional resistance encountered in mechanics. We have fluid friction. It is developed when adjacent layers of fluid body, this is liquid or gas, moves with different velocities. The measure of the frictional force is dependent on relative velocity between the layers, that is called as velocity gradient, and the viscosity of fluid. However, this topic will be further uh, discussed in the course of fluid mechanics, probably in our second year. Now here, uh, what happens that we write down the frictional resistance as a shear stress between the fluid layers, which is expressed for a typical liquid, say water, as shear stress equals to coefficient of viscosity multiplied by the velocity gradient. That's the very simplest form, and uh, this is just as an introduction to you about that fluid friction. Next comes the internal friction. It occurs in all solid materials that undergo cyclic loading. What is meant by cyclic loading? Means you are loading say a steel bar, you are giving a tensile load, again you are releasing the load, again giving the tensile load, like that. For highly elastic materials, the recovery of deformation is associated with very little loss of energy caused due to internal friction. However, there are certain materials of lower elastic limit and it can undergo appreciable plastic deformation during loading. What is plastic deformation? I hope that you know little bit. Just after the yield point is crossed, that also you know, then the material, without much of the force, material goes on elongating. However, what I was continuing, that the internal friction due to such deformations may be considerable. Again, the mechanism of internal friction is associated with shear deformation, and these things will be treated in the course of material science. And also to some extent, we will discuss about the shear deformation, shear stresses, etc. in the second phase of the mechanics, that is mechanics of deformable bodies. Now, uh, let us focus on dry friction. I put this one as the last because this is the most common type of frictional resistance, and this is the topic, or this we will study in the course of basic mechanics. So we are concentrating now on our subject matter, that is the dry friction. So as per the basic definition of friction, dry friction also arises between two unlubricated solid surfaces in contact having a tendency to slide or sliding. Note the word unlubricated because in this case there is no lubrication is associated in the interface. It is just simply a metal to metal contact, and it has gotten a tendency to slide or sliding. Now look at this particular figure. It's a very simple figure, a block of mass A placed onto a ground, and a force P is being applied from left to right onto this block. Now what will happen? You very slowly you increase the value of P. Okay, it is very difficult to do by hand, but anyway, if you try it out, you will be finding out that at a very small force, the body remains as usual. It has got no movement at all, but it is certain amount of force is getting generated at that interface, that means due to the tendency of sliding, because you are tending to move it. So there will be a tendency to sliding, and the tendency of sliding will be obviously along this direction. It will be opposing the basic force which is actually trying to create the sliding. Now we draw a simple free body diagram of this block. So you can see this particular diagram. So this is the resisting force, or we can call it as a frictional force. This is the normal reaction, and F and N combined we consider to be the resulting force. And you look into this particular angle, that's angle phi. So that also is related to this particular one. And as you understand that F by N will be creating certain angle of this reactive force, and we will find at a later stage this phi also represents tan of phi of this represent also the coefficient of friction. So that is the only thing in this particular slide, and we can see now why at the very beginning the block do not move. Just you put a load, it just starts moving. It never happens. Okay. Now in this particular figure 1c, I'm trying to give you one reason. The reason is that these two mating surfaces, what are these two mating surfaces? One at this hatched line, which is the ground, and this blue colored block at the interface, or at the face where it is sliding. Those faces are never smooth. Now smooth is a very relative word. How much smooth? Okay, so it is a relative word. But as I draw and figure, I'm just telling that, well, the smoothness of the lower surface is something like this, and smoothness of the upper surface is something like this, as shown in this particular figure. Now you can see there are the this particular trough and crests in this particular this smoothness curve. So there are the humps, and there is the lowering, and there is then again going to this particular top portion. So like this, it is all spreaded over the entire surface. Which surface? This surface as well as this surface. Okay. Now, when you are trying to push the upper body, then you can see the contact is not taking place at all the places. Just at the contact of these two asperities, there must be certain amount of angle, and that is a reactive force. Means this reaction. Basically, we talk about this reaction. Okay, so you can see two lines I have drawn. One is a normal, one is a tangential direction, another is a normal direction. So R similarly is acting like this. So I have also given R1, R2, R3. So these are the series of R1 R's that is inclined at different orientations, and this particular one at this particular contact points is coming like this. So if I sum up all the component of R along the T direction, that is basically the resistance offered to P. And if I sum up all the normal reactions along the N direction, then that is nothing but equals to the weight that holds the weight of this particular body. Okay, so what is happening? If the surfaces becomes very smooth, then this particular hump won't be that sharp in nature. It will be much more smoother. So what is happening? That if I see the surface is smooth, then the orientation of R is not in this angle. It will be more towards this side. Means what I mean to say, the angle phi will be reducing if the surfaces are smooth, and R will be near vertical. Okay. Now let's look at the next slide. So I have again copied back the earlier figure 1c over here. Now, what I have just told you right now, in the beginning, the irregularities are in closed mesh and offer more resistance to relative motion, because we understand that if this hump at the very beginning is lying over here, this hump is lying over here, okay, this hump is lying over here, and so on and so forth. But as the force P increases, the contact moves closer to the top of the hump. That means this will rise from this place to this place, and relative motion of the block is initiated just when it comes up to the contact point. So this explanation helps us to understand that why less force is required to maintain a motion than required to initiate the motion of the block. Means once it starts, then well, it becomes very smooth. Okay. But just to initiate that starting point, you require certain amount of force, which is normally larger than the force required to keep it moving. Now you can see the second statement, what we found out in the Leonardo da Vinci's laws that was given by the Coulomb and Amontes. The friction force is independent of projected area of contact. That is understood from this particular figure. See, the true area of contact are only the top of the asperities, okay, which is much lesser than the total projected area. Suppose this is a constant width. Suppose this is the distance I am having, just roughly I'm telling. Then 1, 2, 3 only asperities which the body is holding. But see, if I consider the entire length, there will be a large contact area, but that is not actually operating. It is only at the contacts of the asperities that we get the true contact, and which is much lesser than the projected, as I have told you. Okay. Now, so obviously what is happening, these high stresses are generated at this particular asperity points, I mean, where the contacts are taking place. So obviously, if I increase the load of this body, okay, the surface remains same, but I am increasing certain load onto this particular body, then the high stress which is already at these asperities will increase more and more. And what happens, that these top sharp portions of the asperities might crush. Okay, so that is in our in engineering language what you know as an yielding, crushing, or tearing at the point of contact. So that will be the increase in the resulting increase in the true area. So that you can understand, if you increase the load, then the true area increases. So ultimately, what happens, that this friction force is independent of the project area, because in that particular case, your F will increase, but the N and W all are also increasing. Okay. Now, this is a very simple explanation I have given, that what is actually the mechanism of friction by which we can start moving a body after a certain initial lapse. Now, other factors that influence dry friction are molecular attraction at very close contacts, generation of high local temperature, that I have just told you, generation of very high local temperatures, and adhesion at the contact points, and also the relative hardness of the material in contact. Some presence of dart, films, etc. So that is that entire study we are of course not going. We might be uh, ending our study just talking about little bit of getting little bit of idea about that how the friction gets generated. So here we can see the standard curve, what you also know. Okay, that was the body was there at the at this particular point. There was no friction because there was no relative motion. Now you are increasing the value of P, and the friction force, which is of course opposing the direction of P, is increasing gradually. And this particular zone OI is called the zone of static friction. Okay, zone of static friction. And this friction value increases till it reaches I. Okay, so once it reaches I, then what is happening? That just the motion of the body is initiated. That particular point is called impending motion or impending slippage. We'll be considering impending motion, and certain cases we also call the same phenomena as an impending slippage. So when we talk about impending motion or impending slippage, at this point only, that means at the point I, the magnitude of maximum friction is proportional to the normal reaction and written as F max equals to mu s into n. N, you understand, is the normal reaction. I have not defined here. I have defined earlier, where mu s is the coefficient of static friction. However, in the zone of static friction, this particular zone, for any other point excluding I or O, I'm not written, I'm excluding I have supposed, because it is no force is not getting generated at all at this point. The friction force may be determined from the equation of equilibrium. Okay, we will explain this fact later on. But what, and in this slide I would like to emphasize, just simply or blindly don't put F equals to mu s into n. If F equals to mu s into n is a physical scenario, I mean it appears, it is comes from the physics that the maximum friction force can be written as mu s into n only at the impending motion or impending slippage and nowhere else. This particular scenario should be very well known to you, and don't, once again I'm repeating, don't use just like impending motion, I mean don't, just like other than impending motion you write F equals to mu s into n. What I'm telling, if somewhere the friction force is here, then the body is in equilibrium, as I know, because it is an static portion, because the body has not initiated any movement. So therefore, within this zone, you can, the body is in equilibrium, so you simply use an equation in equilibrium to find out the frictional force. But here the situation changes because it is a transition from a static to a kinematic friction. Now, when it start entering into this zone, that means kinetic friction, there is a sudden drop of friction force, and it continues like this. And that we have tried to explain, or we have seen from this earlier slide of the asperities. So after the slippage, the kinetic friction prevails with the subsequent motion, and kinetic friction is obviously it is less than the maximum static friction, but just at the moment of movement we write Fk equals to mu k into n, where mu k is the coefficient of kinetic friction. Okay, where mu k is later. So you understand that uh, just to have the maximum friction force, we always consider the body still in the static equilibrium state, but it is just at the verge of moving to the kinetic friction zone. Okay, so from this slide, what is the ultimate thing we have derived, or we should keep in mind, that F equals to mu into n should be used only at the impending condition and nowhere else. This is, again I am telling, is extremely important. Once again, we refer to the figure 1b, which is again copied from the earlier slide. Now, what we can write in general is that mu equals to F by n. And this F and n is represented in terms of components of R, that is a resultant, as R sine phi by R cos phi, and it gives the value as tan phi. And that too obviously need not to be mentioned that it is at the impending condition. Thus, we can understand just from the visual look of this angle phi, we can gather some idea about the surface roughness. So if the phi is very small, then obviously we understand that asperities are not that high. So that will be a relatively a smoother surface, and vis-a-vis. So this particular consideration we take up just to represent a visual look, as well as to define that mu also can be written in terms of tan phi, where phi we call as an friction angle. Now let us solve a problem to summarize what we have learned so far. Now we consider this problem shown in figure 1b. What do you intend to find out? What is the range of P for which the block is in equilibrium? That means for this mass M, which is placed on an incline at certain angle, I've shown a force P in this given direction. Now, P has got some magnitude. Now, at certain value of P, the block will go up, and then if we reduce the value of P gradually, then at certain point it will be seen that the body is going down. Say for 5 Newton force, the body is just going up, and for 1 Newton force, the body has a tendency to go down. So in between 1 Newton to 5 Newton, the body has got a tendency to slip either on this side or on the downward side. And what is that range? So that we would like to find out. Now, simply for that reason, we have drawn, you can see, two free body diagrams. One is P max, where P max means just at the impending condition, the body has a tendency to move up. And here we are considering a P mean, where the body is again in the impending condition, but in this case it has a tendency to slide downward. As because we are using the word that Pmax is related to the impending condition for moving up, again from the law of physics, we should be very careful in putting the direction of friction force, which will be opposing to the cause, and which should be in this manner. And whereas it is just the reverse, because when it is P mean the tendency of the body to slide downward, then obviously again from the same logic we have the friction force going upward. In between we consider P equals to P equilibrium. Means what is that P equilibrium? It is lying between the P max and P min. So for these two bodies, we can write down the equilibrium equations. One normal to incline, that is n direction, that is written n minus mg cos theta, and that gives you the value of normal reaction to be 849.6 Newton. By the way, you must check my calculations also if I have not done any mistake. Okay. Now in the figure 2b, along the incline, we write this equilibrium equation, and we find out that P max equals to mu n plus mg sine theta, that is 745.4 Newton. In the similarly, Along the incline again for P mean, as because the body frictional force direction has changed, the equation also changes its sign, and this minus mu n plus the mg sine theta equals to gives a value as 235.6 Newton. Look here, one thing I would like to talk about is that in this equation or in these equations, equilibrium equations, we we could write only two equations, one in the normal direction, one along the direction of the friction force. And as a matter of fact, that is the normal convention, that in the friction problems mostly you try to write one along the direction of the normal and another along the direction of the friction force. Well, coming down to our discussion, we find basically we are having how many unknowns? P max or P mean is the unknown, and the corresponding normal force and the friction force is also unknown. So how many unknowns we are having? P max, F and N. Same is the situation for here also, P mean, F and N. Okay, but I have got only two equations to write. So how I can solve for the three unknown quantities? Because of the fact that we do not have any moment equation for these type of problems, because we do not know exactly where the R, the resultant of this F and N is acting. Okay, so for this typical problems, we simplify it to only two equations by use of the impending condition. Once we use the impending condition scenario, then we can easily find out that what should be the value of friction. Again, I'm just telling that at the impending condition only, we can substitute that value of F in terms of impending condition scenario. That is, we can use F equals to mu into N. Okay, so that we have already taken up. This is u mu into n, mu into n. So therefore the equation merely transferred to two unknown quantities, p max and n, p mean or n. In any way we can find out from this equilibrium equation and the other equilibrium equation along the incline, we can find out very well for the p mean. So from this we got two results. So as we discussed in the earlier slide, just have a note that by considering impending motion, the equations 2 and 3 could be solved by substituting F equals to mu into N, which we get from the law of friction. The range of P for which the given body is in equilibrium is this much. That result already we have calculated in the earlier slide. Now, as far as the problem is concerned, we got the results. We have the results with us. Okay. But anyway, let us investigate once again. For any other value P within the equilibrium zone, what happens? Now, as because within the equilibrium zone, we would like to find out what we have, we would only can find out the P, F, and N. Again, three unknowns coming into picture. So therefore, what we do is that we substitute for various values of P so that correspondingly F and N can be determined. That has been done, which is shown in figure 2D in the form of chart. Now, as because we are finding out F, the force of friction, for the equilibrium condition, we can use either of the equations 2 or 3. It doesn't matter. Why? Because in that particular case, we are keeping F as purely an unknown. So if it is coming as an positive sign, then we understand that whatever the direction of friction we have chosen is correct. If we are considering minus, if we see minus sign, then automatically we will be understanding that the direction of friction force should be opposite to that what we have drawn in our free body diagram. Now look at this particular situation. So we have just started from the maximum force P max, and the corresponding friction force is 254 point N, because it is just simply obtained from mu into N. Now as N happens to be the same and mu happens to be the same, then you can see that at the impending downward condition also friction force remains the same, whereas the P value is coming out to be 235.6 Newton. So we have used a green color to show that these are the impending conditions. And as because it is impending condition, for Pmax, use of Pmax, you must be using equation 2, and for use of Pmin, you must be using equation 3. And in between, we have used only equation 2. Or I could have used only equation 3. Or I could have used mixed up 2 and 3. Doesn't matter. Only thing we have to look into the sign properly. So we have used 650. It is coming out to be 650 as Newton as the P value, little lower than the maximum. Then we find this is the friction force. It comes out to be the positive. So friction down the plane. Then again we have 550. It is positive, friction down the plane. We have chosen a value of P in such a manner that we have see that friction force comes out to be 0. That means at this particular point there is no friction. That means there is no tendency to slide either upward direction or the lower direction. Similarly, if we lower down by, I have chosen another two values, you can see this is coming out to be minus and this is coming out to be minus. So what do we understand? Just I reverse the sign of the friction, and that means the friction up the plane and friction up the plane. Okay, so this gives you just an idea of the either how the friction in between the impending conditions are changing. Okay, so what we have learned by solving the problem, if impending condition is considered, it is necessary to indicate actual direction of friction force in the FBD, as magnitude and direction of friction force are known from the physical consideration stated in equation A. If friction force is unknown, not impending condition of course, then we use equilibrium equation. Moment equation cannot be written if point of application of the F and N is not known. And the last one, the correct assumption of condition of impending motion helps us to simplify or to solve a problem as the friction term in the equilibrium equations are known. And that precisely the last point we have used to solve the problem, and we have given a detailed discussion for that one. Let us take another example problem which states what is the minimum force P required to create motion of the blocks. This problem refers to this figure, figure 3a, where you can see there are two bodies. The first body having the weight W1 has got a dimension of 1 meter into 1 meter. The lower body is having an weight W2 and it is placed onto the ground. Now a load P is acting exactly at this point, that is right left, top left corner. So for this particular problem to analyze, we can understand there are three possibilities. One possibility is that when force P is applied, the top block may topple. number one. Number two, the top block may slide over the lower block. And the last one, two blocks, that is the top and the bottom block, may slide together over the ground. So let us examine each possibilities. If we look for the first possibility, the top block may topple, then this refers to the free body diagram shown in figure 3b. So just at the impending toppling condition, the friction force and the normal reaction should pass through the point O, because this is the point where we are assuming an impending toppling. So no other points are coming in contact with the bottom plane. And W1 is the weight of the body and P is the force which we are considering that whether it can topple the body or not. Therefore, as usual at the impending toppling condition, what we are considering, friction and normal force will act as O, as I have told, and also may be considered to act along the perpendicular axis at O. Means in a two-dimensional figure we are seeing O, and basically we can consider a axis perpendicular to O, and we can take moment about the O also if we think in that line. The equations of equilibrium are simple vertical direction, N1 minus W1 equals to 0, or N1 is 1 kilonewton. P minus F equals to 0, or P equals to F1 equals to mu1 into N1. So this is the impending condition we are considering. Okay. So this is the maximum friction force. This particular, at this point, the body can uh, give to the resist the load P, which becomes equals to 350 Newton. The last equation is the moment equation. So if I take moment about this particular point, then P1 into 1 minus W into 0.5 equals to 0, or P equals to, comes out to be 500 Newton. So if we look the 2 and 3, you can see that the maximum force, or the force of friction that can be given to resist P is 350 Newton. After that, the body will just slip. The moment condition shows that for the toppling about this point O, if we assume the toppling about O, then it requires 500 Newton. Obviously, 350 Newton is a lower value than the toppling condition. Therefore, we can say that it is observed the top block will slide before toppling takes place. Therefore, condition 2 prevails. That means number 1 and number 2 we have noted down over here. So toppling is not considered. That means toppling is not a possibility. Therefore, the top block may slide over the lower block. So let us see the third condition in the next slide. Now, next we consider the free body of the lower block, which is shown in figure 3c. And you can see in this particular free body diagram, we are having unknown parameters F1, F2, N2. And we have got two equations that will be, this is the number fourth equation, and this is the number fifth equation. These are the two equations that we can get from this particular free body diagram. Now, we can look into the problem in two ways. One is that we consider F1 to be at impending condition, so that if I consider F1 to be at impending condition, obviously F1 can be obtained the equation of friction, that is F1 equals to mu1 into N1. So therefore we can easily solve for two unknowns, namely N2 and F2. And other way we think of that, let us look at F1, maximum capacity of F1, and then we find out F2 from the equilibrium equation. And if the value of F2 is what, that we have to again analyze. Let us do that. As because both F1 and F2 cannot be at impending condition, simultaneously we are considering F1 is considered at impending condition. As I told you, so F2 has to be determined from equilibrium equation. So F2 minus F1 equals to 0, or F2 equals to 350 Newton. Now let us find out what is the maximum value of F2. So maximum value of F2 will be at the impending slippage condition, that is mu2 into N2, and we get that value as 330 Newton, which is less than 350 Newton. So therefore what happens, or we can ascertain from this value that before F2, F2 has got a maximum value of 330. So obviously when it crosses the maximum value, this particular from the this particular body can slip from the ground level. Okay, before the impending slippage occurs between the top block and the lower block. So therefore from this equation 5 and 6 we can see that the lower block will slide over the ground surface before impending slippage takes place at the interface of the blocks. So we use equation 5 again to correct the value of F1, what we have observed from earlier. So value of F1 should be correct value is 330 Newton, as we have found from this one. And then from equation 5 we get the value of F1 to be how much? Value of F1 to be equals to 330 Newton. So at the F1 the maximum impending condition is 350, but now the corrected value is 330. So obviously it is understood that F1, the top block and the lower block will stick together, and the slippage will take place from the ground surface. Hence condition 3 is satisfied, which is two blocks will slide together over the ground surface. However, one may also investigate the possibility of two blocks may topple together. However, this is a very remote possibility. You can check it, but only thing that you give some dimensions to the lower block so that that moment equation is validated. You can write a moment equation without the dimension of the block. So choose some arbitrary block or dimension, or you can keep the same dimension and see, or you can get an idea that in this particular case, that is the fourth case, the possibility, as I have told, will be in remote, and it will probably won't be possible. Now we consider another situation, slipping and rolling friction. This is primarily applicable to the bodies which are, as I told you, it can be a roller or it can be a wheel sort of thing. So in this particular case, you can see a roller which is acted upon by a load P acting along the handle, and this load P is transferred to the body of the roller as it is shown in this exaggerated figure. This black one is the shaft of this particular attached to this handle, and it passes through a socket placed at the center point of this particular roller, so that this shaft transfers the force P onto the roller body in this direction. So what we see over here from over here is that this P is just decomposed into one horizontal force PH, one vertical force PV, and the roller is moving towards right, for which a frictional resistance between the shaft and the roller is put as an anticlockwise moment m0, and also a friction from the ground is acting just at this particular point, which is just below the center point of the roller. There is a normal force also acting, and R is the resultant force that is acting at this particular point. So the force PH required for rolling at uniform speed merely overcomes what? The resistance from the ground and that at the shaft and roller interface. So at any instant during rolling, there is no relative motion between the roller and the ground at the point of contact. So therefore, what happens due to the rolling, as because there are no relative motion between the ground and the roller contact point, a large amount of friction force is reduced in rolling of a body compared to slippage. Anyway, some resistance is always offered during rolling, but that is smaller than the friction at the impending slippage. That you should keep in mind, that when the body is rolling, then the impending slippage condition friction is much more compared to the rolling friction. However, another point we should keep in mind, that in most of the problems we may neglect M0, as shaft and roller interface is normally lubricated or fitted with bearing. So therefore what happens, the resistance M0 is very small. This particular concept is similar to the concept of frictionless pulley or pin joints, what we have done in our earlier lectures. In this slide, uh, this figure 4b, what was shown in the earlier slide, is again shown here, and it is evident from figure B that when M0 equals to 0, F and pH do not exist. So that is shown in figure 4C. This is very interesting. See, the moment you remove this M0, then what happens? So you assume that M0 is not there. So automatically from the equilibrium equation, we find that pH must be equals to F. And if I take moment about this particular point, then what we are having, that F multiplied by this radius equals to 0. That means there cannot be any existence of F. If there cannot be any existence of F, then there cannot be any existence of pH. So this W equals to W plus PV equals to N. This becomes the only equation that comes for this particular roller, and there are no other forces acting in this horizontal direction. So this is interesting because what it means, that no resistance to roller exists from the ground, and the roller will continue to move at uniform speed without stopping, which never happens in practice. Okay, so why this thing is coming into picture, that is the thing we would like to talk about. Anyway, the roller, what you are seeing in the figure 4C, is commonly known as free wheel. In many cases of the solving problem, such situation will arise for drawing the free body diagram, and in that case we will be calling this particular body is free wheel. But as a matter of fact, in existence there cannot be, or in reality, sorry, in reality we do not have something like that, a free wheel, because it cannot move, it cannot continuously move without stopping. As a matter of fact, what happens, that in reality the bodies in contact will deform, means there will be certain amount of deformation at the lower point by virtue of this load, this roller will undergo certain amount of deformation. So that we are going to see from this particular figure 4D free body diagram. Now only thing, just for making it simpler, well, I have just removed that PV and we are considering only one horizontal force is acting onto the body, and that too it is just to overcome the frictional resistance that comes out from the ground. And we are not considering anything like M0 as we discussed in the earlier slide. So here we have drawn an exaggerated view. We can see an exaggerated view of the deformation, and we are considering certain amount of deformation has taken place in this particular zone. So due to this deformation, what happens? The reactive force R, this particular reactive force, is no longer acting at this particular point. It is shifted towards its right and by a distance A. Okay. So therefore, what you can observe, the entire free body diagram comes out to be like this. Weight W is coming, horizontal force P, and R is acting. That means the body is in equilibrium under the weight load P, or the force P, and the reactive force that is coming from the ground. And this reactive force, again as usual, can be decomposed into one force F, which is basically offering the resistance from the ground, and this is the normal force coming. Now we can see from the free body diagram that W equals to R cos phi. Okay, so what it means, the component of reaction in the vertical direction is merely taking up the load W, and in the horizontal direction P equals to F, and that is nothing but R sine phi. So R sine phi is the resistance that is coming. The P should be overcoming that resistance for rolling, and the weight is carried by the component as shown in equation 1. Now normally the contact area of the deformation is extremely small, so thereby the angle phi is also small, and we can write down that sine phi equals to tan phi equals to A by R. That means this is A, this resistance is very small, A and R. So obviously this tan phi equals to A by R, and combining equation 1, 2 and 3, we get a very simple relationship, P equals to W into A by R. Now here A is the coefficient of rolling resistance, and it has a unit of length. This is very important, okay, that this is called the coefficient of rolling resistance, not the mu that we have just used earlier. That is a ratio of F by N, and here A is a length unit which is called coefficient of rolling resistance. Now you can see for a given load W, if A is very small, then the resistance it is offering for rolling becomes extremely small. So this is a very important conclusion we can draw from this equation 4, that if we engineer uh, some components like that, where the in between deformations of the ground and this becomes an extremely small, then obviously a very small amount of force is required for what, for rolling this particular roller or the wheel, whatever you can say. So so this is a situation which we utilize in our everyday life also. Suppose there is a large weight and we want to move that weight. So we have seen that people put some sets of rollers below that particular body and just push so that the rollers will roll and the body can be moved very easily. Anyway, we will take up an example problem of similar type. Now, I give you an practical example of what is the amount of force P required. A typical electric locomotive to haul Rajdhani Express at 120 kilometers per hour with around 19 coaches consumes only around 3000 kilowatt compared to the weight of the entire train, means 19 coaches and the engine. Okay, this particular 3000 kilowatt is really very low value. Now, how it is possible? It is possible because wheel and tracks of the railways are made of hardened steel, and hardened steel deformed very small deforms by a very small amount. So obviously, as from the equation 4 we discussed earlier, the A becoming very small, so what is happening? The power requirement or the tractive force requirement reduces to a very small value. So therefore contact deformation is small, that I have just written over in the slide, and for that A is very small and resistance to rolling is also very low. Now here in this last two slides we are considering that what happens due to rolling resistance and what happens also certain times it is also some slippage if it is occurring, or for a typical roller body if both slipping and rolling situations can come into picture, and we can also examine what is the real possibility. So just to just to elaborate this discussion, I will be showing you two problems in the next slide. Now this is the first problem, what we can see in this figure. So in this particular figure there is a block which is placed between rollers, okay, and this block can only have a vertical movement and it has got an weight W. This block rests on a wheel or a roller, and it is having a contact at this particular point 1, and W2 is the contact that is having with the ground. Okay, this entire system is having a contact with the ground through the roller at this point 2. Look, for the W1 we are only considering as if that the weight of the block is simply transferred to the roller. So we can see a free body diagram of this figure 5a, which comes out to be in this form. Now what is the problem statement? What is the minimum force P required to roll out the cylinder? Okay, so what should be the value of P so that the cylinder can roll out? Now in this particular case, what could be the possibilities? There are two possibilities: impending slippage at 1 and rolling over the ground at 2. Mind you that at both the point it cannot roll. It has to roll at one point and slip at other point for the given problem. Okay, so either it slips at this point or it slips at this point. So obviously the other way around, if it slips at this point, it will roll at this point, and if it slips at roll at this point, then it has to slip at this point. These two are stated over here. Number one is the impending slippage at 1 and rolling over the ground at 2. So somewhat the roller will roll out as the arrow is showing, and impending slippage at 2 and rolling over the block at 1. In that particular case it will roll out like this. Okay, so I come back to the free body diagram we started with discussion. So in this particular case, the free body diagram, there is an N and there is a friction force F1 coming in this direction and F1 F2 coming in this direction, N2 is the normal reaction at point 2, W2 is the weight, and obviously I'm just putting not W1, I'm putting N1 directly, as I know that this N1 should be equals to W1 without drawing the free body diagram of this particular top block. Now when I consider impending slippage at 1 and rolling over the ground at 2, as usual, we must be very careful about giving the direction of F1. So if it is impending slippage at 1, that means the body is trying to move about in this direction, then obviously F1 acting onto the body should be in this direction. Now, what about F2? I've just put an F2 in this particular direction. However, if I'm considering this F1 to be at that impending condition, okay, then then I have to be very careful about F1, and we will be finding out what is the situation of F2 from the equilibrium equation. Okay, let us go ahead with the solution of this problem, then probably we can discuss much more on it. The FBT of the roller is shown in figure 5b. As I've just told you, the direction must be the opposite to direction of impending slippage, and F2 is unknown and can be determined from equilibrium equation. These equilibrium equations are 1, 2, 3, and the last one here we are using a moment equation about the point O, and that is F1 into this distance 400 equals to F2 into this distance 800. Now F1 is in impending condition, so obviously F1 max is mu1 into A, and that comes out to be 600 Newton. Now from the equation 4 we can find out that F2 is 300 Newton. Alright, so F2 is 300 Newton, and this value of F2, let us compare with the F2 max value. So F2 max value is again mu2 into N2, and that comes out to be 1000 Newton. That means from the equilibrium equation we get 300 Newton as the F2 force when the body is slipping at this particular point. Okay, so this is a very big, this is a very much possible, as because we told that if it is a rolling friction, then that must be much smaller than the impending condition, and this condition is very much satisfied. So we can see that F1 is also greater than F2, and F2 is less than F2 max. The condition 1 is satisfied. To roll the cylinder from equation 3, we get P equals to 900 Newton. So if we apply a 900 Newton force onto this wheel, then you can see the condition 1 is satisfied. It will slip at this point, and it will roll at this particular point 2. So one point it is slipping, and at point 2 it is rolling. So let us examine the second condition, and we go for the next slide. Now here, impending slippage at 2 and rolling over the block at 1. So impending slippage at 2 means in the free body diagram, if there is an impending slippage in this direction, F2 must be in this particular direction. So the direction what we have drawn earlier, or what is have been shown in this particular free body diagram, is absolutely okay. And as usual, we will, in this particular case, F1 will be determined from the equilibrium equation, because we do not know anything of the F1. It is purely unknown, but F2 is known from the impending condition. So F2 max is 1000 that we earlier observed. Okay, and from the equation 4 that is on the last earlier slide, we get F1 equals to 2000 Newton. So here F1, what we got from the, what we have just getting from the equilibrium equation is much more than what is F1 max. That means F1 max means this is the maximum possible friction force the point 1 can hold. Beyond that, the point will slip. And we have already considered a slippage condition at this point 2. So obviously we understand that the cylinder will not roll but slip at both 1 and 2, and from equation 3, the earlier the required force P equals to F1 plus F2, and that is coming out to be F1 plus F2, and that is coming out to be 3000 Newton, which is much more than 900 Newton. So we conclude that cylinder will slip at 1 and roll over the ground at 2 for P equals to 900. Now, so you can see that in all normal cases, we can infer from this particular problem that slipping at both the point requires a much higher load compared to simple rolling. Okay, so rolling will be one point rolling and another point what you call slipping. Well, this is pertaining to this given particular problem, but in anyhow, it is also proved that if it is a rolling takes place, that will be always much more lower compared to the frictional resistance that is uh, coming from the impending condition, much lower than the impending condition. Now we take up another problem where you can see there is a load, and this load is nothing but a beam, a heavy beam having an weight W, and it is resting on series of rollers. I just don't say 4 rollers, it is a series of rollers over which the beam is placed, and we want to push the beam with a force P. So problem statement is determine the horizontal force P needed to push the beam at a constant speed over series of massless rollers. Coefficient of rolling resistance is given at the contact surfaces are for all the rollers taken together, which is shown in the figure 6. See, what is meant by that? This individual has got a coefficient of rolling resistance, and that all together is 0.2 mm. Similar is the situation at the ground level. This is at the beam to roller contact, and this is the roller to ground contact. And radius of each wheel is 15 mm. Now, first we draw the free body diagram of the iron beam, and this shows, and in this particular free body diagram, we are considering one case that this Ws is only the weight shared by a single roller, and similarly Ps is the force required to overcome the resistance offered to the rolling for a single roller only. Okay, so that's the reason we have given the value as Ps. Now in this particular case, obviously the rolling resistance will come in this direction opposing the value of P. This is the normal reaction, and this R1 is the resultant force that is acting at this particular point, and this particular point is this point. So this is from the free body diagram, and similarly, if I can draw the free body diagram for this roller body, then it is just the opposite. R1 is acting at this particular point, and F1 is there's a force acting onto the roller. This is the opposite to this particular direction, and N1 is a normal reaction and acting onto the roller. Look here that R1 is not exactly on the same vertical line of the roller center. It is bit away from this particular vertical line. And what is this distance? This we are calling as A1. So obviously A1 is the coefficient of rolling resistance if I consider a single roller. So here the distance A1 is simply denoting that at what point the resultant reactive force will act. Okay. Similarly, for the ground condition, this is A2. A2 is the distance from the vertical line to the point of action of this resistance R2 coming from the ground. And similarly, we have drawn one force F2, which is the resistance offered from the ground onto the roller body. Now here, this is bit thick black colors. This denotes a certain amount of deformation for which we are getting the distance A2 and A1 respectively at the ground level and at the roller top level. So the distance between friction force F1 and this friction force F2 is approximately equals to 2R because these deformations are normally very small. So incidentally, you can see that this roller becomes a two-force member. Just this is a two-force member. Is it okay? That means the roller is acted upon only by two forces at this point and at this point. So the line of action will be passing through this R1, R2, and obviously you can see this particular point is not going through the center because this A1, A2 are different. Okay. Now, in this particular case, we can write R1 equals to R2 equals to R, we can say, or we just keep it like that. So R1 equals to R2 and the line of action do not pass through the center as I have told. Now the equilibrium equation suggests that PS equals to F1. So as we get from the figure 6a, F1 equals to F2 equals to F, that is from the figure 6b. This is in the horizontal direction. Ws equals to how much? Equals to N1. Ws equals to N1 as we can see from figure 6a, and N1 equals to N2 equals to N figure 6b. Now this is possible because we have assumed the roller to be massless. Okay, so that is also given over here, the massless rollers. And then we use an moment equation, and this particular moment equation is basically, this is N2, this is equals to N, and this is N1, that is also N. So the moment equation comes out to be at the center of this particular roller as N1 into A1 plus A2 equals to 2 into F into twice R. This approximate distance is twice R. Therefore, combining all these three equations, we get PS. That means this particular P value for a single roller comes out to be in the form of F, and that is equals to Ws multiplied by A1 plus A2 divided by 2R. Or for all the rollers taken together, we can consider to be P, and that equals to coming out to be W into AB plus AG by 2R. AB and AG are, as I have told you, is the AB is the sum of all these A1s and AG is sum of all two A2s divided by 2R, and that is coming out to be only 24 Newton. That means only 24 Newton is required to push this 1.2 kilonewton load over the massless rollers. Okay, so this also gives you the idea what we talked about, that locomotive engine and the example of the Rajan Express, that what a small amount of force is required if we consider a rolling resistance, and if we can use the rolling resistance in our actual practice. Now in the green color, I have just given that suppose the roller has gotten weight Wt. Okay, if the roller has given an a Wr, so if the roller has having a mass of Wr, then obviously N2 is changing to N1 plus WR. So P equals to W into AG plus N2 into AG by 2R. So this N2 value only incorporates N1 plus WR over here. But obviously, this is not the free body diagram for this. This is the last part having the roller. Because in that particular case, it will be never a two-force member, but it will be acted upon by R2, R1, and a W, uh, the weight of the roller over here. So automatically, the roller body will be will be having that equilibrium under the action of three forces. So concurrent condition will be giving you the equilibrium of this particular roller body. So here we consider two examples for slipping and rolling resistance problems, and this I hope that you are uh, clear about how to consider the problems when it comes down to and slipping and rolling. So we complete this particular part one of this lecture on friction with this particular slide.